The second building block is what we call a line source or sink. And so we will call this building block number 2. And that's a source or sink. And the right way to think about this is to imagine an infinite line or a line that is emitting or absorbing a volumetric flow rate V dot, that's meters cubed per second, okay? And as the line becomes infinite, so this is a continuous distribution of points. As the line becomes infinite, obviously V dot also becomes infinite. However, in the limit, V dot over L, which is the volumetric flow rate per unit length, becomes finite. And with that, we can just turn our attention into a two-dimensional situation where you just have only a source or a sink. We're going to call this number M, which is V dot over L. And so you have a source or a sink that is emitting or absorbing M, or V dot, or volumetric flow rate per unit length flow out of that point or into that point. And by mass conservation, at any radial location R from the center, because the flow is irrotational, we only have just we're going to assume we have only a UR component, and the distance over here is R, UR. By virtue of mass conservation, so mass conservation, whatever is coming out or going in must go out or go in. And therefore, M is simply equal to 2 pi R, which is the circumference over here, times unit depth. If you think about that's an area, and that times UR. And that gives us UR is equal to M over 2 pi R. And U theta is equal to 0. And from this, we can integrate the potential and the stream function. So let's start with the potential. We have UR in polar coordinates. It's equal to d phi by dr, and that's equal M over 2 pi R. So this gives us phi is equal M over 2 pi log R plus some function of theta, and U theta is 1 over R d phi by d theta, and that implies, and that's equal to 0. So this implies, so if d phi by d theta, we get f prime of theta equal to 0, and this implies that f of theta equal to a constant. We set that equal to 0, and therefore the potential is equal M over 2 pi log R, where M is the volumetric flow rate or sink, suction, so M could be positive or negative per unit length. Now, for the streamlines, stream function, we do something similar. In polar coordinates, UR is equal to 1 over R deep C by d theta, and that's equal to M over 2 pi R. So this implies psi is equal to M over 2 pi times theta plus f of R, and U theta is minus deep C by dr equal to 0. Deep C by dr is f prime of R. So this implies that f of R equal a constant. We set that equal to 0, and then we obtain psi is m over 2 pi theta. Okay. Now again, it's going to be much easier to draw the streamlines, and then from there we can draw the potential. And so if you think of the source over here or a sink, and again this number could be positive or negative, what you're going to have for the, so if you draw the x-axis and the y-axis, okay, what you're going to have for the streamlines, they're going to be at lines constant theta. Okay, they're going to be lines of constant theta, right? And the potential, because this is a truly two-dimensional flow, so psi1, psi2, etc. And the potential, they're going to be perpendicular, they're going to be concentric lines of constant, so log r. Essentially at a given r, they're just going to be constants. The value would be log of that radius, and that's how you get the different, so phi1, phi2, phi3, etc. Okay. Now there's a little variation on this source, which proves to be convenient. In many cases, we would like to move the source to a different location from the origin. So if this were the origin, x and y, sometimes it's convenient to move the source to a point A, B, okay, at a distance, some distance, okay. Now, for a point P, the potential at that point, we can construct it. This would be the absolute location R in terms of the polar coordinates, and this would be the relative location with respect to the source. Let's call this R1. So we're computing the potential and the stream function at point P, okay? And if this is angle theta, okay, this is angle theta 1, then just directly by analogy, phi is equal to m over 2 pi, okay, log R1, so with respect to the source. And then we can express R1 in terms of the absolute coordinates, so you can express it in terms of the position vector R and AB, or do it this way, m over 2 pi log of the square root of x minus a squared plus y minus b squared. And psi similarly is m over 2 pi theta 1, this angle, and that's equal to m over 2 pi into the arctan, so tan inverse y minus b into x minus a. Okay, and x would be the position, x and y are the position for point P. Okay, and we're doing everything with respect to point AB. So x minus a would be, and y minus b would be this distance, y minus b, and this guy would be x minus a. Okay, and this would be useful if you want to place different sources in different locations in a uniform, in a potential flow.